bloque hablaremos sobre los aportes de la academia al desarrollo de los distritos térmicos. A continuación, y para cerrar nuestra agenda académica, los invito a escuchar la conferencia Evolución del sistema de refrigeración de la Universidad de Texas en Austin, a cargo del señor Juan Ontiveros. Él es vicepresidente asociado de gestión de servicios públicos y energía de la Universidad de Texas en Austin. Le recordamos que al finalizar de la conferencia tendremos un espacio para responder todas las preguntas que ustedes nos envíen a través del chat. El señor Ontiveros ha dirigido el Departamento de Gestión de Servicios Públicos y Energía de la Universidad de Texas en diversas funciones desde 1997, que han culminado en su actual cargo de vicepresidente asociado. Es responsable de la producción de energía en las plantas de la universidad, de la distribución de energía producida al campus y de la gestión de los servicios públicos adquiridos, incluyendo el agua doméstica, el alcantarillado pluvial y el gas natural. El señor Ontiveros ha participado en el diseño y la construcción, la ingeniería de mantenimiento, la gestión de proyectos y la explotación de plantas desde 1973. A partir de finales de la década de 1980, comenzó a centrarse más específicamente en el mantenimiento de las instalaciones, las operaciones de la planta, la planificación maestra de servicios públicos, la construcción y las negociaciones de tarifas de servicios públicos. Es miembro de la Junta Directiva y expresidente de la International District Energy Association, IDEA. Tiene una licenciatura y un máster en Ingeniería Mecánica por la Universidad de Texas en El Paso y es un ingeniero profesional autorizado en Texas. Le damos la bienvenida en este momento al señor Juan Ontiveros con su conferencia Evolución del Sistema de Refrigeración de la Universidad de Texas en Austin. Señor Juan, bienvenido y muy buenos días.
Muy buenos días. Con todo gusto estar con ustedes este día. Mi presentación la voy a hacer en inglés.
En inglés,
perfecto. Para que no me falle tanto. Con eso voy a comenzar. ¿Sí la pueden ver?
Sí, señor. Ahí la estamos viendo. En diapositivas también la puedes colocar en pantalla completa como tú desees.
Lo que voy a hacer es talk about the evolution of our system, cooling system on campus. I've been on campus since 1996. With that, I'm just going to jump right into it. What I'm going to talk about is to give you some background. I'm going to try and talk slower, because I know you're trying to translate this. Give you some background about our system, how big it is, how it functions, and really talk about the evolution of our system. This has been an effort over 25 years. This is not overnight. It's taken us a long time to get to the point that we are now. But I'm going to talk about some of the principles and the steps we've taken to design and improve our district cooling system. As mentioned before, I'm responsible for all the power and all the heating on campus as well too, but I'm primarily going to be focusing on the cooling systems. And I'll show you some of the results of our efforts. Let's see, hopefully that works. Can you see that? ¿Sí la ven? Our system consists of 5 chilling stations and 2 thermal storage tanks. The chilling stations are 63,000 tons, and we have about 10 million gallons of thermal storage. Chilling station 3 is 3 chillers, totaling 11,000 tons. Chilling station 4 is 3 chillers with 9,000 tons. Chilling station 5 is 3 chillers, totaling 13,000 tons. Chilling station 6 is 3 chillers, totaling 15,000 tons. And 7 is 7 chillers, totaling 15,000 tons, plus a 600-ton heat pump chiller. The heat pump chiller is primarily designed to provide hot water to a medical district. Chill water is stored in 2 tanks. That gives us a 22,000 tons.
I'm sorry, Juan. Can you hear me?
Yes.
Estamos viendo tu presentación, pero con el fondo negro. No sé si podrías ponerla en modo presentación.
Está en presentación. Otra vez.
Creo que es donde dice Display Settings. Perfecto.
Let me do it again.
Intentemos nuevamente.
Hacerlo otra vez.
Puedes intentar en la opción de pantalla completa.
A ver si la ves. ¿Sí la ves? ¿La ves?
Aún no la veo.
No, déjame ver otra vez.
Ahí, la dejaste de compartir, pero la puedes compartir nuevamente para que la veamos. Ahorita como estaba bien, lo único era la configuración de la presentación
otra vez
como tal.
¿Dónde va a batallar? ¿Sí? Los perdí.
Aún no la vemos. Puedes darle en el botón compartir en la parte inferior.
Tengo que hacerlo otra vez. No agarro bien. No veo StreamYard. Ahora sí la veo. La pierdo cuando lo pongo en Presentation View.
Porque ahorita cuando lo estabas compartiendo, estábamos viendo bien la pantalla compartida. Acá ya la tengo nuevamente.
¿La ves o no la ves?
Ahí está, sí, en la parte de arriba donde
dice background. Settings, ¿dice background?
Está, lo que pasa es que vemos la vista con fondo negro, el mapa y la imagen, pero eso es ya la configuración del PowerPoint como tal. Creo que en la parte de arriba donde dice Display Settings.
Sí. Swap Presenter View.
Podemos intentar con esa primera, creo que ahí sería perfecto. Ahí está muy bien, ya puedes continuar nuevamente.
Perdón
Tranquilo, muchas gracias, Juan. Adelante.
Sí, so our system consists of 5 chilling stations and 2 thermal storage tanks. You can read down the list of chilling stations that we have and 2 thermal storage tanks. So because our chilling stations are large, these 17 or 18 chillers serve the entire campus. And so I'll talk a little bit about how our system is configured. So this is a screenshot of the campus, and our power plant is right in the middle of the campus. And we have 5 cooling plants that are distributed around the campus. These 5 cooling plants are all connected by a tunnel system, which I'll show you in the next screen. And then we have 2 thermal storage tanks. And you can see one is towards the north part of the campus, one is toward the south part of the campus. So our campus is about 20 million square feet, about 160 buildings. And we produce all the energy. So all of the energy we produce is natural gas, about 3.9 million MMBTUs a year. And we distribute a lot of electricity, so 338 million kilowatt hours a year. So our system, this is a screenshot of our cooling system. The purple lines that you see there are our tunnel system, and there are four cooling the plants are right here: chilled station 4, chilled station 5, chilled station 6, chilled station 3, and chilled station 7. 7 is the newest one, and I'm going to show you later on a video of what that chilling station looks like. But the snapshot this day is a relatively cool day. It's 70 degrees, but we're producing 16,000 tons, 10,000 kilowatt hours, and 33,000 gallons a minute at this instant. We cool 24/7 all year round. Even in the winter, we have a cooling load because we have computer systems and labs throughout the campus. So at this particular snapshot, where the total kilowatt per ton for the whole campus is 0.6. And you can see there are these large yellow boxes. That's the cooling plants. And then you also see down here in numbers here, you'll see delta P. So these are pressures. So what we're doing, I'll describe our strategy and how we, because you produce the energy in the cooling plant, and then you also then distribute it out to the relative buildings. And so all this total combined is what we're measuring here. And you also see that we have the 2 thermal storage tanks. At this particular time, we're not using them, but you can see chilling station tank 1 has 66 feet per minute thermocline. So these are 110 feet diameter tanks. So 66 feet of water there. And this one has 77 feet of water, 72 feet of water. So the way this is to give you an example of, so our cooling is my largest load for electricity. As you can see, our peak load cooling is about 30,000 tons. So it's it's my single largest electrical load on campus. So we have to pay much attention to how we do cooling. Cooling is between 30 and 50% of my total load anytime, all during the year. So I have to pay attention to it. So this is a history of our total kilowatts per ton historically from 2000 down to 2010. And you can see we've been gradually improving it year over year by various strategies. And now I'm going to go a little bit into some of these strategies that we've taken. The biggest drop that occurred to us was in 2009. And this occurred when we used to use steam turbine-driven chillers to do cooling, because this is something that I inherited. They were very old, very inefficient. So when we got rid of them, converted to electrical, it really improved our efficiency down to where we were in 2010. So, so to give you an idea, in 2007, we had 45,000 tons of capacity because we added 15,000 tons. So we added a new cooling plant. We decided to build this new cooling plant with VFDs, but our intent was to try and optimize the cooling plant. But I wanted to run the plant a year without it and then see how the optimization improved our operation. So our average kW per ton in 2007 was 0.84. We had 15 million row square feet that we were serving on campus. Campus has grown a lot in the time that I've been there. Our peak power megawatts was 59 megawatts, and our peak cooling was 29,000 tons. In 2008, we started to optimize the plant. And basically, I'll go into a little bit of detail as the principles behind how we did that. But by optimizing, we immediately cut 0.04 kilowatts per ton. So we also added about almost 1 million square feet to the campus. And so our loads grew a little bit. So I'm going to talk about the principle that we apply to optimize. And so there's a relationship of RPM and lift to energy. And I'll describe what lift is in a minute. So RPM, so the power ratio is equal to the RPM ratio, but it's cubic. So, and lift is the differential pressure is related to speed squared. So bottom line is if I can reduce speed in a chiller from 2,000 to 4,000, from 4,000 to 2,000, and it's a 1,500 horsepower chiller. What happens is, because it's cubic, I reduce horsepower 8 times. So that's a really important principle. You want to run, instead of running chillers at full load, you want to run them at part load, and because by varying the speed, because you get a tremendous improvement in horsepower needs. Lift is similar. So if I'm originally 80 psi, and the lift that I'm talking about is really the difference between chill water temperature and condenser water temperature. That's the cooling tower temperature. So if I'm at 80 psi and I can lower the speed here, I can actually get, by reducing it to 20 psi, I save it's 1/4 of the pressure. So I save it saves a big factor in reducing efficiency. So let me describe how this works. So you have cooling tower water that you're producing, and you have the chill water temperature that you're sending out to your loads. So if you're at 100% of load, this is what it is. So the only way to reduce lift is lower the tower water temperature or raise the chill water temperature. That's the only two ways to reduce lift. So if you take you increase the chill water temperature to 46 degrees, that's 90% of the design lift. By getting 90% of the design lift, you save 85% of power. If I lower the tower water temperature and raise the chill water temperature both, now I'm at 21% of design lift. That's only 10% of the power because of the cubic relationships and the square relationship. So it's really, really, really important to understand this principle. So the other part of designing the cooling plants is you have a lot of options in terms of how you connect the chillers to your system, and then how you connect your cooling towers to your system. So there's variable primary that you can do. You can decide to header each chiller into one big header, or have dedicated pipes that go out to the system. You can do a variable primary, you can do a primary, you can do a secondary, and you can do a constant primary. So in the condenser water, you can do variable flow, you can do constant flow. So those are the options. So I say that the most efficient modes is you do a variable primary, you can do a variable flow on the condenser water temperature. That's the way you're going to do this. So the principle that we use, understanding this and working through this, the approach that we took on this new cooling plant. This is a 15,000 ton plant. You can see it's a very constrained space. It's right around the middle of a bunch of buildings. This is a computer science building. This is our power plant. And but the concept was everything would have VFDs. So that is the cooling towers, cooling tower pumps, the chillers, and the chill water supply pumps. So everything with VFD. We would use no control valves to modulate flow through the chiller or the evaporator. So because you put in a valve, it actually creates a flow restriction, and you lose efficiency. So we would only use control valves to modulate the flow across the 3 cooling towers. That's it. That's just to help us balance it. It was a very challenging plant to build. It's a very constrained site. And one of the challenges that we had here is that the tower really ended up being smaller than we wanted. And later on, I'll explain what the problem that created. So this is what the chillers look like. There are 3 chillers. Each one's a 5,000 ton York OM. And this is the VFD. So it's a 4160 VFD. These are big motors. These are 4,000 horsepower motors. So this is what we put in the plant. So the concept, so what we learned is that because the tower is limited, even though it's a 15,000 ton plant, I could only deliver 12,500 tons. And because the tower limited me. And there was also issues with, I had no choice on where to put the plant. I had to put it in a particular spot on the campus because of restrictions in space. And so it's feeding a very old, feeding our tunnel system. Some of the pipe is been around since the 50s, and this particular lines were restricted. So I created problems. So that we wanted to do is we want to modulate the pump speed and output the new chilling station to control our loop pressure. So if I pump, what we actually learned is that we were actually spending more energy pumping water out to the campus than actually using in the chiller. So we had to figure out a strategy to resolve this. So what we decided to do is we wanted to reduce the chill water loop pressure. By that I mean is you send water out, that's supply water, you have return water coming back. What is the differential pressure between the two? So we wanted to reduce the chill water loop pressure because I wanted to reduce pump horsepower. And the reason is if you have too high a pressure in the supply, what ends up happening is your control valves in your buildings cannot sustain the pressure. If it's too high a pressure, the valve lifts. So what ends up happening is you're creating a false cooling load. It's overcooling the building. In our system, the way we offset it is we actually then had to reheat it with steam and then cool. So now you have a battling system, cooling and heating battling each other. If you lower the pressure, the valve works. It doesn't get overcooled. You don't have to use the steam. So the other thing, by modulating flow, the speed of the chillers and the pumps, what you do is you actually improve your maintenance costs by adjusting that and how often you do maintenance. Because by not running them at full load all the time, they're running cooler, and so they're going to last longer. So that's another advantage that you get. And so you basically, by doing this also, you improve your plant performance and you reduce your pumping costs. And bottom line, I'm a utility, so I sell the electricity, steam, and cooling. So I have chill water rates, and so if I can lower my rates, I also save money for the campus. So money they pay for me for energy is money the campus cannot use. So I have to reduce my rate. So that was another of our objectives. And so what we learned out of this process is that we're actually using more energy to pump than we're using in the chillers. So this is why we had to do this. And the way we evaluated it is I have a real-time hydraulic model of the campus. So what you're seeing here, the light blue lines and are basically our tunnel system. It allows me to see all of my conditions. I can see, looking at pressures, flows. And so what it helped us identify was that this is where the new chilling station was built. Right here is a snapshot increase of it. And the red lines, what it's basically saying is that I have really high flow, too high a flow. So it's restricted flow. So I have a bottleneck in the system. So we were over pumping by trying to use chilling station 6 too much. So our objective was to lower the pressure. So what we did was, over a winter, we decided to test how low we could take the pumping pressure. So we started lowering our delta P 1 psi an hour, lower and lower. Every hour we lowered another psi. And what happened is we actually went to 0 delta P. In other words, supply, water, temperature, pressure, and return water pressure, where the differential was 0. And no one complained. None of the buildings had any issues. So it showed us that we had an opportunity by lowering the pressure, that we actually did have an opportunity. So this first chart here that you see here is 2010. So what we learned is we actually saved almost 9,000 gallons per minute by just lowering the pressure. And then the next year we looked at what were the pump savings. So the pump savings was $200,000 at those energy costs in those years. So it showed this is really, really a big opportunity. Now, remember what I mentioned is that if you have too high a pressure, that the control valves in the buildings do not work. So what ends up happening is the building gets too cold. Well, what ends up happening is you're dumping that cold water back into your return water temperature pipe. So what ends up happening is you have a lower delta T. So So what ends up happening is if you lower the pressure, you don't get too cold. You don't dump that cold water in the return water temperature. So what we saw in 2011, we could see that by lowering the pressure, this is without improvements, by lowering the pressure, we saw a 13% to 25% improvement in delta T. If you improve your delta T, you're improving the effectiveness of your chiller, and in our case, also significantly improving the performance of the cooling tower, of the tanks. So this was a very big deal. We could see that in the initiative. So here's what happens. And so by also resetting temperature, so condenser water temperature is 71, the chill water supply temperature is 39, degrees lift, 32. If I increase the supply from 39 to 44, lift improves 18%. So what we decided to do also was we wanted to adjust the supply temperature. In the past, historically, we had always sent chill water always at 39 degrees. But in the winter, you don't need 39 degrees. You can go warmer. And so we decided we wanted to adjust the supply temperature dynamically. And the way we did is we put it's a straight line adjustment in our control scheme based on wet bulb. If it's really humid, I've got to get more cold water out to the buildings because I'm extracting humidity. It's very humid here in Austin. If it's winter or drier, I don't have to send as much chill water. I can adjust the chill water temperature up. So again, I want to reduce that lift. So what we basically did is we used the model to say, okay, where are our bottlenecks? And what we learned is that chill station 6, which was in the middle, we wanted to use it a lot because it was very, very efficient. It was the most efficient plant at the time. So what we decided to do is we'll take it up to, remember I said it was 15,000 ton plant, but I really only could do 12,500 because of the tower. So we'll take it up to 12,500. Once we reach that point, we start to lower it. And what happens then is we use the other stations to control flow. So this controls pressure, the other stations control flow. And so basically the way our system works is it tells our operators start a chiller or stop a chiller. A load is grown. And so what they then do is they dispatch it based on which chiller is available, making sure that it's available, and which one is the highest efficiency. So it's dispatched. Once they start it, then our control system really then starts to control the speed. And I'll go into a little bit here in a minute and show you how that works. So by doing this, what we learn is that we reduce our peak cooling 3,000 tons. And I don't have to do the reheat because I'm reheating steam, using steam to reheat because it got too cold. I actually reduced our steam by 30,000 pounds an hour. So we saw that immediately. So what we're doing now is this is what our current conditions are. So our delta differential pressure between supply and return is 8 psi in the peak of summer, and it's 2 psi in the winter. I don't need as much chill water. So to give you a perspective, I used to see the delta P's of 70 psi. So it's a bunch of horsepower. So what ended up happening is we actually reduced our pumping energy 1,500 horsepower. And by resetting the temperature from 39 to 44, we cut our kW per ton from 0.72 to 0.63. Immediately, we could see that. And so we also decided that normally thermal storage tanks are dispatched based on time of day. So you charge the tanks at night and use them during the day. And usually it's based on time. Because we have this optimization system, we use optimum energy. We decided we wanted to do this dynamically. So what is the exact best time to charge the tank? When is the exact best time to discharge the tank? And so we have one tank that's primary, and then when we run out of it, then we run the secondary tank. So that's the way our system is designed now. By doing that strategy, we reduced our peak campus load by 4.2 megawatts. So then we said, okay, well then I produce power, I produce cooling, I produce heating. Let's use, we did a weather forecast. We did a linear regression of weather and cooling load and power loads for 3 years. And we developed regression curves. And so we're using, basically, we can do a pretty realistic projection of weather for 3 hours. And we use that to predict our power load. And then we use that to dispatch the chilling stations and the TES to meet it. So the bottom line, what this has created so far is it's saving us about 29 million kilowatt hours a year. That's about 72,000 tons per year of reductions in our system. So with this, I'm going to show you a little video of our chilling station 7. So one of the big advantages we had for this, let's see here. Big advantages that we had with this plant is that we could build the exact cooling tower that we wanted. So we decided to build the plant with a 5-degree approach. So it's a much bigger tower. And in actuality, we've been able to run most of the year, we run with a 2-degree approach. That really has helped us make this plant really, really efficient. So this chart shows you a more extensive look at how we've done our performance. So in 2008 is when we put in chilling station 6. It was 0.79 kW a ton. The dotted line you see here is the campus, how many tons of cooling are we putting onto campus? You can see how it grew. This period here where it grew was when the medical school was built. So you can see we've been gradually reducing it through the years. And so in 2019, we ended the year at 0.59 kW ton. That's total, including chillers, towers, pumps, everything, the whole thing, the whole campus. If you look at our cooling plant performance, this is total energy to campus. This includes electricity and steam, but you can see it's about 325,000 MMBTUs. And our kW ton, how it performed, even though we were adding the same amount of energy, we were using less power to make that cooling. This next chart is looking at it a little bit differently. This is on a per square foot basis, divide the energy per square foot. This is energy to campus. And you can see we reduced it about 24% at this point. The goal line is our total efficiency. And what that is, basically it's kilowatt hours, ton hours, and pounds of steam, and converted to BTUs, divided by the fuel we buy. How many BTUs of fuel we buy. So that's so you can see we actually finished the year at 2019 at about 90% efficiency. So you can see as we improve our efficiency, our fuel use goes down. So energy costs go down. So over this period of 96, we've saved 21 million MMBTUs. And that's equivalent to 1.2 million metric tons of CO2 that we've been able to offset. So with that, I'd be happy to take any questions.
Muchísimas gracias, señor Juan, por esta presentación. Como usted lo sabe, tenemos un momento de preguntas. Justamente vamos a invitar en este momento a la doctora Rita Cristina para que nos acompañe. Ella es directora del Centro de Investigación CIDARE. Rita, bienvenida de nuevo. Qué rico que nos acompañes. Te voy a ceder este espacio pues para que hagamos esta ronda de preguntas con el señor Juan Ontiveros.
Thank you very much, Laura. Thank you very much, Mr. Ontiveros. It's really a pleasure to have you here again, sharing all your knowledge and experience with us in this conference. So it's very impressive, this presentation, just to see how the efficiency of this massive system has been improved through all these years. So I have a few questions. So
Okay.
First, how low does the temperature goes in Texas during the winter?
Yes, so the cooling tower water, the lowest we can take it is 58 degrees.
Yeah.
Because it affects the chillers. And
yes.
So what we do, the way our optimization system is designed, we work with the equipment manufacturer, the chiller manufacturer, and say, what are its ranges? What is the max and min? Because we don't want to trip the chiller. We don't want to lose it. We don't want to damage it. So the lowest we can take it is about 58 degrees. And so it used to, when we first started doing this, none of the chiller manufacturers wanted us to vary the condenser water flow. They said, no, you can't do it. It's impossible.
Wow.
And so we had to fight for it. And we finally did get it. And so we actually were able to take the flow very, very low and get it to 58 degrees. Well, that's a tremendous improvement in lift. And so you're taking advantage. So you got 58 degrees, and the highest we take our chill water temperature is 44 degrees. So that's the lift. Raise the chill water temperature and reduce your tower water.
Yeah, that's great. So, and have you ever considered doing some free cooling during the winter?
Yeah, so what's interesting is we don't have a lot of winter.
Yeah.
So our winter is only 3 months. And so I don't have enough time to be able to pay for free cooling. So with the fact that we can lower our condenser water temperature and we raise our chill water temperature and we adjust the flow of the chillers, I can produce chill water in the winter at 0.32 kW a ton. That's the same as free cooling. But I'm doing it with chillers. And so this last February, we had a big freeze, and it was a big factor that affected Texas. And we were able to run. We never lost our plant. We had everything on the whole time. And we were running the whole campus with 4,000 tons. One chiller was serving the whole campus. And so we can do from 30,000 tons or 35,000 tons to 4,000 tons. And that's because of our variable ability to use variable frequency drives.
That's impressive. Really, really impressive. So I saw that you have two big thermal storage tanks, and they use chilled water. Another possibility is just to use ice also. Did you consider both, and how
Why not?
you choose? Yes, how did you choose
Yes,
chilled water over ice? Yes.
Yeah. So here's the issue. To make ice, you got to go to 32 degrees. So I couldn't use my existing chillers. I would have to replace them or build new ones. That's one part. I wanted to be able to leverage what I already had. That's the first part. Second part is to put in an ice making chiller. Their efficiencies are not very good. They're like 1.2 kilowatts per ton. And so if you look at the potential efficiency of an ice making chiller, because they're higher, they use ammonia, they're higher compression, and they have a lot more losses. It takes a lot more energy. Whereas my chillers are at 0.5 kW ton. So over long term, it's cheaper to put in water, and I don't have to replace chillers. And so that's why we went with water. Plus the other point to remember is my understanding is that ice making systems, ice chill water, ice using systems, storage systems are a lot more difficult to manage because those chillers are problematic in using them. They can be challenging. Whereas chill water is actually very simple. I can run my actual chill water through the tank. I don't have to have a plate frame heat exchanger. So I don't have to worry about freezing. I don't have to worry about using glycol. I don't have to worry about any of those things. My chill water actually flows through my tanks and through my buildings.
Thank you, Mr. Ontiveros. I have a couple of questions here. One of those is, does the university campus have any energy certification?
Yes. So buildings, all of our standards when we build new buildings is LEED silver. But our system was the world's first university to get certified PEER. So the U.S. Green Building Council has what's called a PEER system, PEER, Performance and Performance of Electricity Renewal. That's what it's called, PEER. And it's a very challenging certification. It's based on reliability, efficiency, cost effectiveness, risk mitigation. It's very involved. And we are certified. And so when a building goes trying to pursue PEER, a LEED, we actually they get almost 18 points for free because of our system. And so we are certified on PEER. We were the first university in the world to do it. And we certainly, last year, we recertified and we're platinum.
That's really, really impressive. Yeah, I have seen other campuses doing like kind of some improvements, but this is really the most impressive I've ever seen. So I have another question. So could you tell us if you consider relevant any safety risk situation for people in the operation of a district energy system?
Yes.
Perhaps the use of refrigerants?
Yes. Yeah, that's a good point. So all of our refrigerants are 134A. We have some R22 still in 2 chillers, but primarily all is 134A. And so one of the things that safety is a very important thing for me, because safety of my people, safety of students. And so, yes, we have refrigerant monitoring systems built into each one of our chiller stations. So they monitor if there's any inadvertent leak, and it's tied into a system where if, let's say, a significant leak develops, what happens is it automatically alarms, lets the operators know that there is a leak, because one of the problems with refrigerant is it can cause you to have a heart attack if you have too much refrigerant. It's a heart sensitization agent, so it can cause you to have a heart attack. So it's very important to me to make sure that people are safe. So it alarms them, lets them know, and you get out. And what it does is it rolls up the doors of the station and turns on fans and ejects the refrigerant into the atmosphere, so that my people are safe, and then we can go back and fix it. Now, the good thing is I've never had to use it. We've never had a leak. Because the other part of it is my people are also very conscious about it. So they go around with manual sniffers every day, and they try to find a leak if there is a leak. So most of the leaks are very, very small. It's a fitting that went loose or something like this. So they try and catch it, because refrigerant is very expensive. My 5,000-ton chillers have 17,000 pounds of refrigerant. You don't want to lose it. It's a lot of money. And so if there's any small leaks, they try to catch it, because we are actually required by our environmental regulations to report any lost refrigerant. And so we have to report it. And so it's part of our emissions. So yes, it is very important that you put in refrigerant monitoring and evacuation systems in your cooling plants. And make sure that you do not put a boiler in the same plant unless it's separated. Because what happens is when you burn refrigerant, it turns to phosgene. Phosgene is poisonous. It's the most poisonous poison there is in the world, phosgene. So if you burn refrigerant, it turns to phosgene, and you can kill people. And so you don't want it. So our boilers you saw some boilers in the video, but they're in a separate room with separate ventilation systems, so that they're not connected.
Thank you so much. I think I have time for perhaps one question more. So I was wondering whether you involve your students, I said perhaps undergrads or graduate students, in these improvements that you made on the plant, and whether those results are published in some articles.
Yeah, so it's very difficult for us to involve we have a lot of experience, and we have a lot of data. We have a historian, so we actually gather 1 second data, and I have 1 second data that goes back to 2006. And so you could say we're very nerds about data. So we look at data a lot, and that's how you monitor performance. You can put all these things in, but if you don't know monitor performance, you're never going to improve. You don't know how well you're doing. So we do use students, but we typically bring them in to learn about our system. We help them doing in data reduction, data analysis, but it's very difficult to bring them in because their safety issues. Our power is 12,000 volts, and our steam is 700 degrees in the plant. So there's concerns about safety. So our people are the ones that manage it, and we do all our own maintenance. We do our own operations. And so, yeah, in 45 years of doing this, I've never had an employee die on the job. And I want to keep it that way. And I don't want students to die either. So yeah, we do work with professors, we work with students, and we do projects, but not necessarily in improving. It's more about analyzing.
Okay, so I think, we don't have more time for questions. So thank you very much, Mr. Ontiveros, for this impressive speech about your campus improvement. Thank you so much.
Yeah, and if somebody has some more questions later on, my email's there. They can email me. I'll try to answer. If I don't know the answer, I'll pass it on.
we'll do that. Thank you.
Thank you. Thank you.
Muy bien. Muy bien, pues muchísimas gracias a Rita Cristina por este